Hi everybody, and welcome to this new episode of SageMaker Fridays, Season 4. My name is Julian, and I'm a Principal Developer Advocate focusing on AI and machine learning. Once again, please meet my co-presenter.
Hi everyone, my name is Ségolène and I'm a Senior Data Scientist working with the AWS Machine Learning Solution Lab. My role is to help customers get their ML project on the right track in order to create business value as fast as possible.
All right, great. Thanks again for your time. Thanks for helping us prepare this. So, this is once again a long demo, right? And we have a pretty cool use case today. If you have questions, please ask all your questions. We have friendly and expert moderators who are waiting to help. So please ask all your questions, and there are no silly questions. Don't be shy, and make sure you learn as much as possible. Okay, that's our only purpose today. So, Sego, what are we doing today? Last week and the week before, we actually covered recommendation. We covered fraud detection, and I think today we are zooming in a little bit on healthcare and life sciences. So tell us more.
Yes, and so this week we are going to work on classifying medical images in order to detect cancerous cells.
Okay, so pretty serious topic.
Pretty serious topic. Pretty serious data sets.
Pretty serious data sets, and of course. Healthcare and generally life sciences are an area where AI and machine learning are making a big difference.
Exactly.
Right. So it's really cool that you get a chance to talk about that today. This is the notebook we're going to use on GitHub. So go and take a look. We'll show it again at the end of the session. So don't worry if you didn't have time to catch this one. Okay. So let's dive into the demo and the use case right away. So let me show the actual notebook. Okay. So Sego, what are we doing today? Okay. So we're using medical images and we try to predict whether there's a problem in there. But tell us more.
Yeah, exactly. So we are going to use some images, medical images, and we are going to apply deep learning model on it, on top of this data set, and we are going to be able to detect if there is a metastasis or not in the image. Okay. So the data set we are going to use for this demo comes from the Chameleon 16 challenge. So the raw data provided by the challenge has been processed into 96 pixel tiles. The tile dataset is the original dataset is over 6 gigabytes of data.
Okay, yeah, so that's pretty big.
That's pretty big, but in order to easily run this demo, the dataset has been pruned to the first 14,000 images, and of course comes included in the repo with this notebook for convenience.
Okay, so we can see some
exactly.
We can see some images here on screen. We'll don't worry, we'll look at the notebook in detail, but just to give you a clear picture, exactly. Yeah, not intended of what we're trying to do. We're trying to learn if those pictures show normal cells or if they show cancer cells.
Exactly, and these color images were extracted from histopathologic scans of lymph node section, and as you can see here, each image is annotated with a binary label indicating presence of metastatic tissue.
Okay.
So label 1 metastasis, label 0
probably bad news, unfortunately.
Yeah, bad news, and label 0.
You're good. Okay,
you're good.
So hoping we have lots of zeros, but yeah, unfortunately, not always the case. So these are small images, by the way. Yeah, you mentioned 96 by 96.
Yeah, 96.
So not a lot of pixels. But still, let's see how well we can do. And of course, working with small images is always better when it comes to training time and how much compute you need, right? And so intuitively you would think, oh, we need high res, 4K by 4K images, but for some applications, yes, you do need that. Satellite images, very high res images. But in fact, for most computer vision applications, we can actually get good results with small images and get them quicker, right? So again, let's see how well we're doing here. What about? Let me go back to maybe the first few cells here. We import some libraries. We download the data set, and yeah, as you can see, this extract is about 350 megs, 69 megs actually. So not huge, right? We download it locally, we extract it. So we see exactly what you said, 14K images, 96 by 96. And of course,
3 color channels.
3 channels, because red, green, blue, right? So that's the shape of that data. And of course, we have the labels 0 or 1, okay? And then we upload that stuff to S3, right? And we delete the local copy just to save space, but of course you can explore those images locally if you'd like. So in fact here we don't do any data prep, okay? But let's step back, okay? Because of course here the images are already labeled, okay? So in real life it's not always the case.
It's not always the case, no.
Okay, so let's imagine, you know, we work for a hospital or, you know, our research lab, we would get plenty of patient images, and then doctors or researchers would actually look at those and say they're okay, or no, unfortunately they're not okay, they show cancer cells, and so they need to be treated as such. So here we have 14,000 images, which is small data set for computer vision, but if we had to go and label all of them ourselves, that's a lot, right?
Yeah, exactly.
And who wants to look at 14,000 images and say 0, 1, 0? It's a lot of work. So how can we help customers if they have to do that? If they're working with their own data and they have to label it? Is there a service we can use?
Yeah, I think that we should use, in this case, SageMaker Ground Truth.
Okay, so let's jump just for a second to the SageMaker console, and we see, let me zoom in a little bit, and we see this capability called Ground Truth. And Ground Truth is, and let's just go and enter this one. It's been specifically built to help you label images. Okay, so we're not going to do the demo right now because there's a lot of stuff we want to cover today, and we like to focus more on training and tuning the model. We'll actually do that later. Probably we'll show you that in a future episode when we revisit the operations aspect of machine learning, and I guess we'll go back to this example. So really quickly, again, the 30-second whirlwind tour of Ground Truth would be, you can create a job, a labeling job, okay, and as you would expect, your data needs to be in a S3 or a storage service. So you would upload your images, your raw images to S3, okay, and then you can create the actual job, and we have some built-in task types, okay, and we have images and text and video, why not? Okay, and we can also do point clouds, which is really important if you're doing complex things like autonomous driving. 3D point cloud, super cool. But okay, not our purpose today. Okay, so when it comes to images, we can do image classification. So we can create a task where a team of workers that we create, could be people. Employees, right? Yeah, a private team. Employees of the company. It could be labeling partners, so companies that are AWS partners specialized in labeling, and it could also be Amazon Mechanical Turk if you needed to scale your labeling efforts to maybe millions. In this case, you probably need experts.
Exactly. Yeah.
Expert labelers, right? Because it's not as simple as saying, well, this is basketball or soccer, or yes, there's a human in the picture. This is really very complex stuff, and you don't want to label them wrong. Right? Yeah, exactly. The consequence could be bad. So in this case, you would have a team of doctors, or I don't know, medical students, all the experts you could find. and you create that team and you distribute the work, right? And so they would go and visualize individual pictures and label them. In the case of classification, you can apply single label, multi-label. So if you're looking for multiple pathologies, you could actually say, I'm seeing this and this and that, okay? You could do bounding boxes if you wanted to do tumor detection, for example. Instead of just flagging it, say, yeah, this is the bit in the picture where, you know, it's not good. You could do segmentation if you wanted to actually identify all pixels of a particular area, etc., etc. So super simple. Again, we'll probably do a demo in a future episode, but that's the kind of tool you would use for labeling. And yeah, you just need to define your team. You just need to define. You just need to upload your data, define the task type, provide some basic instructions, and then all the labeling team gets access to a portal where they actually start seeing images, labeling them, and then you get that output in S3, and that's the label data set you can use. Okay, so again, very cool thing, but we'll probably come back to that. Okay, SageMaker ground truth. Okay, so we don't need to do this here. We have the labeled images, and we don't really need to do data. Okay, so what we probably need to do is to split, right? To split and for training and validation. Okay, so we just do that pretty easily using this API. So we have 11,000 images for training, 2,000 for validation, and we keep a test set for benchmarking, 1,000. Okay, so now we have those three data sets. I guess the next question is, how do we feed those images to the algo that we're using? So we could very well we could pass them as a file tree, so to speak, an object tree in S3. Okay, so that's possible. But it's a lot of files, right? And for convenience reasons and performance reasons, we don't want to have to deal with thousands of files. And again, this is a small data set. Imagine millions of them, right? Copying, moving them around, making sure none is missing. You know, the more you have, the more painful it is.
Exactly. Yeah.
So one step we're going to take here is we're actually going to pack those images into a single file, per data set. Okay, so we'll have one large file for training with all the images in there, same for validation, same for testing. Okay, and that makes it more convenient to move around, to archive, version, if you're working with different versions of your data. And it makes it easier and more efficient to send to the training instances, and maybe to split if you use distributed training, which we might be doing later. Okay, so if you have one big file, you can split it in chunks and send the chunks to the different training instances instead of sending individual files where you get a lot of let's say I/O overhead, working with thousands, potentially millions of files. So this is what we're doing here, and so we're using a file format which is called record IO, which is actually part of Apache MXNet. And there's an equivalent format in TensorFlow. If you're familiar with TensorFlow, you've certainly seen TF record files. Same story. Okay, we pack small instances into one single file. Okay, so that's what we're doing here. So here we're reading all our images in each data set, as you can see here, training, validation, and test. Okay, and we write them in record IO format into a single file. Okay, and we can apply extra quality compression. If we have really large images, we can shrink them, etc., etc. Okay, and we save images in JPEG format. Okay, so it looks a little complex, but that's really what we're doing: reading images, writing them into a record structured file. Okay, and actually we get two files. Once we've done that, we can certainly see them here. So for example, we see that we have an IDX file, which is an index file, and this is actually a text file that gives you the offset of each image inside the bigger record IO file. Okay, so so that's pretty simple. So we see all our training images. So if we want to go and grab one particular image, we know where it sits. And of course, the record IO file is a binary file with all those images packed into it. Okay, so just this is generic code. As long as you're feeding it, you know, NumPy arrays, it works. Okay, ND array is just the equivalent of a NumPy array in MX. So, but that's pretty compatible. So you can reuse that code as is, I think. Okay, so we do this 3 times. Okay, so now we have our 3 record IO files. We upload them to S3. Okay. Of course, we have labels, forgot to say, but that's obviously we have the labels in there as well. And now we're ready. Okay, so you know, compared to previous episode, it's we don't do data prep, we don't do feature engineering. We just do, we just package the images to make them easier to work with. So let's get to the really important stuff now. So which algo are we going to use here?
So as you see here in the code, we are going to use a building algorithm of SageMaker, which is the image classification algorithm. So this building algo is a supervised learning algo that supports multi-level classification.
Yeah, we can actually look at that. Here's the SageMaker doc,
and it takes an image.
It's called image classification algorithm. So you kind of know, you kind of know what it does. It's a good name.
It's a good name, yes, exactly. And actually, it's going to use a convolutional neural network, the ResNet, that can be either trained from scratch or trained using transfer learning technique, especially when a large number of training images are not available.
Okay.
So yes, it can be run in 2 modes. So full training and transfer learning, we will see that. And in full training mode, the network is initialized with random weights and trained on user data from scratch.
Okay.
In transfer learning mode, and this is important because we are going to use it today, the network is initialized with pre-trained weights, and just the top fully connected layer is initialized with random weights.
Okay, so yeah, it's a good question to ask. So we're using ResNet, which is well-known. Efficient image classifier. It's been around for a few years now. It works very well. People understand it pretty well. But in this case, do we train from scratch or do we start from pre-trained weights? Because we have 2 classes, right? 0 and 1, and we have 14,000 images. So I haven't checked how balanced they are, but that we have thousands of samples for each class, and the images are not really big. They're not super complex. So in this case, we will be starting from a pre-trained model, okay, and see if it works. Because if we look at the images once again, we see, I would say, basic geometrical shapes.
Exactly.
Yes.
Yeah.
We see, circles. We see diagonals. We don't. Obviously, there's complexity in there, but you could say, well, medical images. These are really different from everyday life images that you would find in the ImageNet dataset, which is usually what we use for pre-training. But again, the basic patterns that we see here, right? Like we see, like diagonals, we see, dots, we see circles, we see ovals, we see textures, we see color gradients. These have probably been learned by the pre-trained model. So it's worth a shot.
Exactly.
Yeah, it's worth a shot. Let's do transfer learning. Let's just train for a small number of epochs. Let's see what kind of accuracy we get.
Exactly.
Okay. If it's not too good, then I guess we could start from scratch. And again, for demo purposes, we have a small number of images, but if we use million of images, you know, maybe we could train from scratch. But you know, it's a balance. It's a balance between training time and you know, budgets and everything. So here we're going to try. So let's go back to this. Okay. And so we use that image classification algo. As you mentioned, it's ResNet. Okay, it's built in. So we just retrieve the container because training and for that matter deployment activity in SageMaker is based on Docker containers. But in this case, it's already there. So the only thing we need to do is grab its name. We need to find the number of training samples that we have, the number of classes that we have, because obviously these are hyperparameters. So let's take a look at those hyperparameters. Okay, so the first one is number of layers, and of course, again, they are, you know, available in doc, so you can go and read them, right? Some are required, some are optional. Okay, so my advice always the same: start with only the required one, get your baseline, and then start tweaking, right? And then if you don't want to tweak, use model tuning, but we'll see that later. Okay. So what did we set here? So 50 layers for ResNet. ResNet 50.
ResNet 50.
It's kind of the mid-size model. You could do 18, I think, is the smallest.
Yeah.
And the biggest is 152, I think. And let's check. What am I guessing? Let's number of layers.
Is it first?
No, it's not going to be the first one. Come on.
Yes, yeah. 50, 152
we
or
could
200.
do, okay, yeah, for transfer learning, we can do from 18 to 200.
200.
Okay, and for data with small image size, just selecting 20, 32, 44, 56, 1. Okay, fine. So we're doing transfer learning. So we're kind of in the middle. Okay, 18 is going to train much faster, but accuracy
maybe
could be lower because we have fewer parameters to learn. 200 is going to be much lower, but potentially gives you better accuracy. Okay, so let's go with 50, which is a reasonable first attempt. Let's see what we get. Okay.
Yeah, to create a baseline.
Yeah, for now we're trying to get a baseline and then see, you know, can we use classification on this problem? We're trying to get a quick sense of, is there a machine learning solution to this? And if we get good accuracy, then we can go crazy with bigger models
and iterate again
and iterate on larger networks. Okay, so we use a pre-trained model.
Yes, say one.
Okay, so set that
0.
Yeah, so 0 means start from scratch. 1 means weights are pre-initialized. Augmentation type. So tell us about that one. What does that do?
So that's super interesting indeed. This is hyperparameter in the image classification algorithm is super interesting because the input images can be augmented in multiple ways. So what does it mean here? Crop color transform. So you're gonna have some random transformations, such as including rotation, shear, and aspect.
So we're actually creating, we're adding new samples that are tweaked, distorted, altered.
Exactly, yeah. And this will help the algorithm to generalize better, especially since we are dealing with medical images. So
yeah, I think it's a good idea to have this one here because you can see, you know, color, lighting, color, weather, you know, for example, this one here. So, you know, I'm guessing, I'm not a doctor, obviously. I'm not sure which particular area is of interest here, but it's not dead in the center, right? Depending on how that picture was taken, you know, the area of interest could be somewhere in a corner or, you know, these are not pixel perfect picture taken by a professional photographer. Okay, they come from, you know, machines, etc., etc. Maybe they've been cropped. Maybe you know, maybe that's the interesting bit, or maybe that's the interesting bit, and you know, it's not always going to be nicely in the center for you to examine. So yeah, image augmentation is a good way to create let's say, slightly more hostile samples that help your model learn better. You make the model train harder, right? Okay, so good one. Okay, image shape we've already discussed. Number of classes is pretty obvious. Number of training samples we already know. Okay, and then we have a few machine learning parameters. Batch size. So we have how many do we have in the training set? 12,000? 11,000. Okay, so 64. That's fine. It gives us hundreds of batches per epoch. So it's an okay starting point. But what if you use 32 or 128, right? Epochs, 5, which is a reasonable low number. We're doing transfer learning, so we shouldn't be training for longer than, I don't know, maybe 10 is the max. But just a handful of epochs. Learning rate, the hardest of all parameters to pick. So we'll stick with this, which I think is actually the default value in the doc. You find it. Where is it? Oh yeah, sorry. Learning rate. I think it's 0. Oh no, 0.1 is the default. Okay, so we actually try a slightly lower learning rate, which makes sense for transfer learning, right? Because, you want to fine tune. You don't want to make huge adjustments. You just want to specialize for. And precision type. So we're training with 32-bit weights for maximum precision. We could speed up training and reduce model size with load 16, but again, not a huge concern. Okay, and again, there are plenty of other parameters, but these are the ones that are really important. Okay, so now we need to configure the training job. So, and we're going to use that estimator object. If you've seen previous episodes, or if you're already working with SageMaker, it's really central. Here we're using the generic estimator for built-in algos, but we have specialized estimators for TensorFlow, PyTorch, etc. So we pass hyperparameters. We pass the location of the training container that we found. The role is for permissions. Access to S3, access to the container, etc. Infrastructure requirements. Okay, so here we are doing distributed training, because why not? So we're using 2 single GPU instances. Okay, so P3 is a GPU family, and 2XL is the entry level size. So they have 1 GPU, but we have multi-GPU instances as well. Okay, so 2 instances will collaborate. Volume size is how much storage each training instance gets. Okay, so here by default you only get 5 gigs, which might be a little small. So I don't think we need 100, but okay, it's just for safety, let's say. Okay, because we'll need to copy the data set, we need to save the model. We could be using checkpointing, so we have different checkpoints for the model, etc. 100 honestly is probably a little too much. Max run is the maximum training time, so 10 hours. Again, that's a little too much. We're not going to need this, as you'll see. And then the output path. Okay, where do we save the model? Okay, so algo hyperparameters, estimator parameters for the training job. And we could train right away. Okay, so we could call image classifier.fit, passing the location of the training set, the validation set, as we've seen before, and we would train a single job. Right? And we've done this in again the previous episode. But coming back to my batch size and learning rate, we know from experience these have a huge impact on accuracy.
On the image classification algorithm, especially.
Yeah, especially. So. Okay, feel free to train a single job and see what accuracy you get. And then how do you do better? So you can do better with this Hyperparameter Tuning capability in SageMaker, which is one of my favorite features, because one, it's super easy to use. So for lazy people like me, it's awesome. it does the work for you. You can fire up your tuning job. And pretend you're working, and then you can report really good results, and you haven't done anything. SageMaker has already done the work for you. So the way this works is super simple. So you define hyperparameters that you want to optimize on, right? And you define ranges. Okay, so for example, here I'm saying, hey, I'd like to explore batch sizes between 16 and 128. Okay, so these are discrete values between 16 and 120, integer values. And I want to explore the learning rate, which is a floating point value. So we use a continuous parameter. And we like to explore from 0.0001 to 0.0, right? Which are again reasonable values when you're fine tuning. And I can specify that this should be explored using a logarithmic scale, because I'm not really interested in trying 0.0002. I really want to try the different orders of magnitude. So I'm really saying, hey, go and explore those different orders of magnitude. Don't go and try 0.00015 and 0.00017. It probably doesn't make sense, especially early on. I want to get a quick sense here of, okay, what's the kind of learning rate I need to use here. Okay, and then we can keep tweaking, of course. And we can run successive tuning jobs where we zoom in on very high performance parameter ranges. But here we're just trying to get a sense. And then we define the tuner, where we pass the estimator that we created just above, with the metric we would like to optimize for, so validation accuracy.
Which is the ratio of the number of correct prediction
to
the total number of prediction made.
Absolutely.
Important.
Parameter ranges, how many jobs I want to run. So here I'm only running 20. No, that's not too much. That's not a lot. I'll get back to that. We don't need much more. I'm going to run them 2 by 2, right, to speed things up. So, you could run them sequentially, but you can speed up a little bit. And yeah, a prefix, a base name for the tuning jobs. So before we actually go and run it, let's talk about the strategy here. So what really happens here? So what happens here is, so we're going to train those first 2 jobs. Okay. And of course, initially we start for the first job, we randomly select values here. Okay. And we see what kind of accuracy we get. Okay. And then we apply machine learning optimization, Bayesian optimization, to pick the next set of hyperparameters to try. So we get a second data point, right? And here the data point is really, what accuracy do I get given that pair of batch size and learning rate values, okay? And so you apply optimization to that, and you pick another set of parameters. And now you have 3 data points, and 4, and 5. And so gradually, you can estimate where to look next.
Exactly.
Okay, and this is super efficient, and generally, it converges quickly. There are other techniques for hyperparameter optimization. There's one called grid search, where you explore systematically. You divide those parameter ranges in grids. And you pick values in all the grids, and you systematically explore. So that works, but it usually takes 10x, right? You can argue on that one, but probably 10x as many, 10x the number of jobs to get similar results. So it takes longer, costs more.
Oh.
Yes. So I'm not only lazy, I'm very cheap. Okay? And so should you be, because it's your money you're spending here. I don't pay my bills, as you know, my AWS bills. I pay the other ones. There's another technique called random search, where we pick parameters at random, and you think, oh, that sounds completely stupid, except this has been proven to work better than grid search. And one of the authors of that paper is Mr. Yoshua Bengio, If the name means nothing to you, is you won a Turing Award for AI contributions not so long ago. So I will not argue with that. Okay, not today, not tomorrow. And so, but random search again generally takes more jobs. So in a nutshell, Bayesian works pretty nicely. You can try random. There's an extra parameter here that sets the strategy. By default, it uses Bayesian, but you can use random, and that's a good baseline as well. So if you don't buy my Bayesian works better pitch, try random, and then go try Bayesian, and then ping me, okay? And if it still didn't work better, yeah, ping me anyway. We'll figure out what's
happened.
Okay, so that's how you do it, and then we define our training inputs, and then we train.
Right.
Yes. Okay, but don't go too fast. Yeah, I just want to show you that actually, running a tuning job is not more complicated than running a standalone job. Configure the estimator, define your ranges, define those few things here. Okay, so that's the only extra stuff you need to do. And then you call fit, and then we'll see what happens. Okay. Okay. Now, yes, you are right. When we selected our training inputs, compared to previous examples in the past few weeks, we have this new parameter that says input mode pipe. So what does that mean? Default is file mode. File mode copies the training set to the training instances. Okay, so we just, whatever we have, we copy to the training instances and they start training.
Okay.
So that's fine, but if you have a big data set, it could take, even if you have fast network, if you have multi-gigabyte, tens of gigabytes, yeah, you need some time to copy. You need to provision space on the instances, as we've seen with that volume size thing earlier. And let's say you have a terabyte data set.
Ouch.
Okay, do you want to copy 1 terabyte over the network?
No.
Especially to multiple instances, because if you have a 1 terabyte data set, I'm guessing you're going to distribute it. And do you want to provision 1 terabyte of storage on each training instance, even though it's not super expensive? No. So what you want to do is stream. Okay, so you don't download, you stream. Okay, and this is what pipe mode is. So we don't copy, we stream the data to the training instance. So lots of good things about that. First, we waste no time copying. So training pretty much starts immediately. And even if we have super huge data sets, we can train. If you have technically, if you have a petabyte data set, it works, right? Because you don't need any storage on your training instance, so there's no limitation there, and the dataset doesn't need to be loaded in memory. So you kind of decouple dataset size and storage size and memory size on training. So you can scale out to lots of even smaller instances because they're only getting small chunks at a time. So
this pipe mode, okay.
Yeah, so pipe mode is super cool. Once you start moving to, let's say, gigabyte scale data sets, it's a good technique. Okay, and record IO makes it very simple to split because we have this record structure in the file, so it makes it easy to split and create the chunks and send them to instances. See, it all works. We thought about this. Okay, so we call fit. We call fit. What now? Lots of dots. Okay. And yeah, an exclamation mark that says I'm done.
I'm done.
Okay. So what happened there? So what happened there is we started running those training jobs 2 by 2, like I said, initially picking random values for hyperparameters and then using the clever optimization techniques to figure out the next, and hopefully over time converging to better models. So where do you visualize results? Okay. Because you don't see a training log here, because keep in mind we did train 20 jobs. Okay, so when you have a standalone training job, you get your training log. When you run fit here, you don't see the training log in notebooks. It would be super confusing to see those 20 logs. So you can easily use this hyperparameter tuning job analytics. It's a very long name, but simple object, to actually extract all the results, okay, as a pandas data frame. And here I sorted them by descending objective value. Okay, so we see that the top job reached 0.90 something percent validation accuracy, which is a very good starting point. Okay, and we can see this is job 13, right? In the 20, or probably it's the 14th, I guess. I don't know. Do we start at 0? Yeah, we start at 0. Okay, so it's the 14th job. So it took a little while to converge to this. Okay, and then the next ones didn't get any better than that. And if we look at the first few jobs, for example, job 0 was 87%, and job 1 was 88. Job 2 was again close to 88. Job 3, 87. So exploration, and 5, 6. Oh, this is better. Okay, so 6 got better.
11.
7 was a bad bet. Okay, we explored too far in that hyperparameter space, so not so good. 8, a little better. 9, a little better. 10, not great. 11 got better. 12, not so good. But see, step by step, and of course, it's not a linear process. It's just, we kind of explore and take bets on those parameter values. But, we got to 90+%.
Always iteration, right?
Yeah, and if we trained a little more and if we explored and tweaked more hyperparameters, we could certainly do better. Then, of course, we could add more data. We could try a deeper ResNet, right? But training time here was, as you can see, very short. It's about 4 minutes. 4 minutes, something like that. Yeah, about 4 minutes per model. Yeah, you see the seconds here. 3-4 minutes. So that's okay. That's, for experimentation, it's pretty good. And of course, we see the winning learning rate, so to speak, was this, and the batch size was this, and of course, we would have never thought of using that, right? I don't think so. Okay. So anyway, and we can see, the super tiny learning rate don't really work. Right? The worst one is actually I think the lowest learning rate of all. So yeah, we can see, okay, this is too tiny. So maybe we could restrict the range and run another tuning job to explore maybe a more meaningful range, right? We see the top 3 models are kind of, in the same area. So we may want to explore it. Okay. You can also go to the SageMaker console, and you can see hyperparameter tuning jobs. And okay, so we see the 20 jobs here. We see the best one. Of course, same results. Okay, and so we see all the hyperparameters. And if we want to see the actual training log for this one, we'll find it down there. Okay. So the logs that you actually see in the notebook also are pushed to a CloudWatch, our monitoring service. So you can actually, and we see 2 logs because we have 2 training instances, right? And yeah, of course, here you can see the log. You can see checkpointing was actually running automatically, so that's good, etc. Okay, so super easy to use. So this is how we're almost at the end. So to sum things up, this is how you can easily train a classification model. And summing things up, what did we really do here? We started from a bunch of images. Okay, so already labeled. But again, in the future episode, we'll do we'll show you labeling with SageMaker ground truth. Okay, so no processing in here. With real life images, probably you would train them. I'm guessing those original images coming out of the medical equipment are high res, so you could just resize them automatically, and then you train and split. We use a record IO format because we think it's cool, we think it's efficient, it's easier to move the files around, it makes it easy to split them. You could work with your image hierarchies if you wanted. We put them in S3. configure the estimator with that built-in algo, with the hyperparameters that we saw. Okay, and then we could train a single model, but we go with model tuning, and we enjoy this run for an hour, by the way. And we can go and do something else. Of course, we're not slacking. We're never slacking. Tuning is just not an opportunity to do other interesting things. Exactly. That's who we are. and then we see results. Okay. So really not difficult. So so if you have your own medical images out there, I'm really hoping we have machine learning engineers and data scientists who work in healthcare and life sciences organizations and companies. Go and try it. Go start from that notebook, tweak it, tear it apart, add your own images, and see in a couple of hours what kind of results you can get. Okay. As you can see, it's really not super difficult, and maybe you can come up with a very impactful results, and yeah, we certainly hope that you achieve them, especially for that kind of application, okay, which are so important for everybody. Okay, so let me show you, and yeah, forgot to say, of course, we could deploy the model, we could automate all of that. And we'll come back to that, okay? Exactly. In those future episodes. Let me show you that slide again. Here we go. Okay. In a few weeks, we'll come back to automation, and we'll show you how to run complete automation of this. Exactly. Okay. And we'll talk about deployment and predicting and other things. Okay. So once again, this is the notebook we use today. I hope you learned a few things. I hope you got your questions answered. And we'll see you next week for another cool use case on recommendation again, but this time for the retail industry. Okay, so we hope you're going to join us next time. And Sego, thanks again. It was a really good one, I think. really important one. Very important use cases. So go and help people get there. Okay. Until next time, thank you very much for watching, and we'll see you soon. Bye-bye.